May 4th, 1945. North Atlantic, approximately 200 nautical miles northwest of the Shetland Islands. Korvettenkapitän Adelbert Schnee grips the periscope handles aboard U-2511 as the crosshairs settle on HMS Norfolk, a 10,000-ton British cruiser cutting through moderate seas at 18 knots. Through the lens he observes destroyer escorts flanking the warship, their screws churning white water as they sweep in standard convoy protection patterns. His fingers rest on the fire control trigger. 6 bow tubes loaded, 23 torpedoes in the magazine. The hydraulic reload system tested and ready. He has 500 meters of perfect firing position, having penetrated the destroyer screen completely undetected, despite their active sonar pinging methodically through the depths. The mathematics are flawless. At this range, with the Type 21's advanced fire control computer linked directly to the GHG passive sonar array mounted beneath the keel, Norfolk represents a statistically guaranteed kill. The programmed firing system has already calculated the solution, accounting for target speed, bearing, distance, and sea conditions. One salvo of 6 torpedoes launched in rapid succession would intersect the cruiser's path with 97% probability of at least 3 hits. The hydraulic loading mechanism could have all 6 tubes reloaded within 10 minutes, ready for the destroyer escorts racing to investigate the explosions. But Schnee does not fire. 3 hours earlier, at 1400 hours, a radio message from Admiral Karl Dönitz had reached U-2511 through the snorkel antenna extending just above the surface. Cease all offensive operations. Germany had surrendered. The war ended not with battle, but with silence crackling through underwater cables. Schnee lowers the periscope with mechanical precision. He orders the electric motors to silent running mode. 2 Siemens Schuckert G-Phi 232/28 units, producing 226 horsepower each, virtually undetectable, even at close range. U-2511 descends to 150 meters, far below the depth at which conventional U-boats could safely operate, and slips away from the British task force at 5 knots. The destroyer escorts never register her presence. Their Type 144 sonar equipment, capable of detecting conventional Type 7 U-boats at 3,000 yards under ideal conditions, returns nothing but ocean noise from the hydrodynamically streamlined hull that cuts through water with almost no acoustic signature. 3 weeks. Germany's revolutionary Type XXI Elektroboot, the submarine designed to reclaim dominance in the Battle of the Atlantic, becomes fully operational just 3 weeks before unconditional surrender. The timing represents one of warfare's most profound ironies. This vessel incorporating technology that would define submarine design for the next half-century, capable of performance that would have devastated Allied convoy operations in 1943, enters service in May 1945, when Germany's defeat has already become mathematical certainty. The story of the Type 21 is not about what happened. It is about what might have been if this submarine had arrived 2 years earlier, when the Atlantic campaign still hung in balance and when German U-boats were sinking. Allied merchant ships faster than American shipyards could replace them. November 1942. Paris, France. Admiral Karl Dönitz convenes an emergency conference with German naval architects and submarine designers in occupied France. The meeting takes place against a backdrop of mounting crisis. Allied centimetric radar has made surface operations increasingly lethal for conventional U-boats. Aircraft equipped with ASV, Mark III systems can detect surface submarines from 20 miles away in any weather conditions. The Type 7 and Type 9 boats that form the backbone of the Kriegsmarine submarine fleet were designed in the 1930s based on principles dating to World War I. They are not true submarines but submersibles, surface vessels that temporarily dive to escape detection or launch attacks. Their underwater performance is abysmal. Maximum submerged speed of 7.6 knots. Submerged range of 80 nautical miles at 4 knots before battery depletion. Underwater operations limited to 18 hours maximum before surfacing becomes mandatory to recharge batteries using diesel engines that require atmospheric oxygen. These limitations have become fatal vulnerabilities. By late 1942, Allied hunter-killer groups patrol the Atlantic with scientific precision. Destroyer escorts equipped with improved sonar maintain contact with submerged U-boats, while aircraft overhead wait for the inevitable moment when depleted batteries force submarines to surface. The mathematical reality is devastating. German U-boats must spend approximately 20 hours surfaced for every hour submerged at combat speed. During those surface hours, they are visible targets for radar-equipped aircraft that can arrive within minutes of detection. May 1943 will validate Dönitz's fears completely when the Kriegsmarine loses 41 U-boats in a single month. Casualties so catastrophic that submarine operations temporarily cease in the North Atlantic. But in November 1942, standing before engineering diagrams spread across tables in occupied Paris, Dönitz already understands that conventional submarine design has become obsolete. He needs something revolutionary. The answer has been developing since 1940 under Dr. Helmuth Walter, whose hydrogen peroxide propulsion system promises underwater speeds exceeding 25 knots without requiring atmospheric oxygen. The Walter turbine uses high-concentration hydrogen peroxide decomposed through a calcium permanganate catalyst, producing superheated steam at 450 degrees Celsius that drives turbines at 20,000 revolutions per minute. Test vessel V-80 demonstrated 28.1 knots submerged during trials in 1940, performance that seemed to solve every tactical limitation plaguing conventional U-boats. But the Walter system consumes fuel at catastrophic rates. A submarine using perhydral propulsion for continuous operations would require a hull so large or a range so limited that practical deployment becomes impossible. Additionally, the system remains mechanically unreliable with frequent catalyst degradation and steam turbine failures. Dönitz demands alternatives. Engineers present a compromise solution. Instead of revolutionary propulsion, they propose evolutionary optimization. Take the streamlined hull form developed for the Walter boats, which reduces underwater drag by 60% compared to conventional designs with external ballast tanks and deck guns protruding into the flow. Eliminate all surface running optimizations because this submarine will spend 99% of its operational time submerged. Install triple the battery capacity of Type 7 boats by integrating batteries directly into the lower hull structure rather than mounting them as separate components. Add a snorkel system allowing diesel engines to recharge batteries while submerged at periscope depth, eliminating the vulnerability of surface running entirely. The proposal represents a paradigm shift, not a submersible that occasionally dives, but a true submarine that occasionally surfaces. The engineers estimate this Elektroboot design could achieve 17 knots submerged versus 7.6 knots for Type 7. It could operate underwater continuously for days rather than hours. It could sprint faster submerged than most Allied escort vessels could pursue on the surface. Dönitz reviews the specifications with growing excitement, but he asks the critical question that will haunt the entire program. When can serial production begin? The lead engineer, following pre-war construction methodology that emphasizes thorough testing and incremental refinement, provides an answer based on sound engineering practice. Design completion. By January 1943. 2 experimental prototypes completed by mid-1944 for extensive sea trials and debugging. Serial manufacturing commencing late 1945. First operational boats delivered to combat flotillas by mid-1946. Dönitz's response is immediate and unequivocal, unacceptable. By 1946, Germany will have either won or lost the Atlantic campaign, based on battles fought in 1943 and 1944. He demands accelerated production, skip the prototype phase. Use modular construction techniques adapted from shipbuilding innovations developed by Albert Speer's Armaments Ministry. Divide each hull into 9 prefabricated sections, manufactured at inland facilities beyond Allied bomber range, then transport sections by canal to coastal shipyards for final assembly. This method could theoretically reduce construction time to 6 months per vessel. The engineers express reservations. Modular construction without prototype testing risks quality problems. Complex systems like hydraulic torpedo loading and integrated sonar arrays require extensive debugging that cannot occur if the first boats off the production line are simultaneously serving as prototypes and operational vessels. But the reservations are overruled. Germany's strategic situation allows no time for engineering caution. The design is finalized in January 1943, designated Type XXI, with production scheduled to begin immediately. The Type XXI represents the most sophisticated submarine design of World War II and the template for all post-war diesel-electric submarines until nuclear propulsion arrives in the 1950s. The hull form is a work of hydrodynamic engineering that would not be matched until computer-aided design becomes available decades later. Unlike conventional U-boats with external ballast tanks creating drag-inducing irregularities, the Type XXI uses a figure-8 cross-section pressure hull with ballast tanks integrated into the lower section. Every external surface is streamlined. The deck gun, a standard feature on earlier U-boats, is eliminated completely because surface combat has become suicidal. Anti-aircraft weaponry is mounted in remotely controlled turrets on the streamlined sail, rather than in exposed positions requiring crew exposure. The dimensions tell the story of ambition. Length overall, 76.7 meters. Beam, 8 meters. Draft, 6.32 meters. Surface displacement, 1,621 tons. Submerged displacement, 1,819 tons. These numbers represent a submarine 30% larger than the Type XXI workhorses that conducted most Atlantic operations, requiring substantially more steel, labor, and industrial capacity to construct. But the performance gains justify the investment. Propulsion combines proven diesel-electric technology with revolutionary implementation. On the surface or at snorkel depth, two MAN M6 V40/46 KBB supercharged 6-cylinder diesel engines produce 4,000 horsepower total, driving generators that charge the massive battery bank or provide direct propulsion. The batteries represent the Type XXI's transformational innovation. The lower hull section contains 372 individual lead-acid cells, triple the capacity installed in Type 7 boats. These batteries weigh 180 tons, 1/10 of the submarine's total displacement, but provide stored energy sufficient for extended underwater operations that would be impossible with conventional installations. For submerged propulsion, two Siemens Schuckert GU 365/30 double-acting electric motors generate 5,000 horsepower total, more power than the diesel engines produce. This configuration reverses the traditional submarine design philosophy, where diesels serve as primary propulsion and electric motors function as limited endurance auxiliary systems. On the Type XXI, electric motors are primary, with diesels serving as battery charging stations. At full power, these motors can drive the submarine to 17.2 knots submerged, faster than many Allied destroyer escorts can achieve on the surface. For silent operations where acoustic stealth matters more than speed, two Siemens Schuckert GV 232/2 8 motors produce 226 horsepower each, allowing movement at 5 knots while generating almost no detectable noise. The performance specifications reveal capabilities that would have altered the tactical balance of the Atlantic campaign fundamentally. Maximum submerged speed, 17.2 knots for 60 to 80 minutes before battery depletion. Silent running speed, 5 knots sustainable for 60 hours continuously before recharging becomes necessary. Range at silent running speed, 365 nautical miles. Snorkel charging time, 3 to 5 hours to restore full battery capacity. Surface range using diesel propulsion, 15,500 nautical miles at 10 knots. maximum diving depth, 280 meters, nearly double the 150-meter depth limit of Type 7 boats. These numbers represent revolutionary operational capability. A Type 21 departing Norwegian bases for the Atlantic convoy routes could transit the dangerous Iceland-Faroe Gap, completely submerged, snorkeling just 3 hours daily for 5 consecutive days, while maintaining 5 knots continuous progress. Allied aircraft patrolling these waters would detect nothing. Radar coverage becomes irrelevant when the submarine never surfaces. Even if detected, the Type 21 could evade pursuit by sprinting underwater at 17 knots, faster than most escort vessels could maintain in heavy seas, creating a probability cone of possible locations that expands faster than searching forces can cover the area. The offensive armament matches the defensive capabilities with innovations that would have devastated convoy operations. 6 bow torpedo tubes, the standard German 533mm diameter, represent 50% more launch capacity than Type 7 boats mounting 4 forward tubes. But the revolutionary element is not the tubes themselves, but the hydraulic reload system designed specifically for rapid salvo firing against convoy targets. On conventional U-boats, reloading a single torpedo tube requires approximately 10 minutes of manual labor by crew members using block and tackle to position 1,500 kilogram weapons within the confines of a rolling submarine. The physical demands limit sustained firing rates and require surface time to prepare weapons for subsequent attacks. The Type 21's hydraulic system eliminates manual handling entirely. Torpedoes stored in the forward compartment rest on hydraulic pallets. After firing, the tube reloading sequence begins automatically. Hydraulic arms withdraw the next torpedo from storage, align it with the emptied tube, and ram it forward into launch position. The entire reload cycle for all 6 tubes requires just 10 minutes. Less time than conventionally loading a single tube on a Type 7. The tactical implications are profound. A Type 21 approaching a convoy could fire 6 torpedoes in initial salvo, reload completely within 10 minutes, fire 6 more, reload again, and launch a third salvo of 6 within 20 minutes, total elapsed time. 18 torpedoes against a convoy containing 40 merchant ships with 8 escort vessels represents mathematically devastating potential. The torpedo loadout provides 23 total weapons, sufficient for 3 complete 6 torpedo salvos, plus 5 additional shots. The torpedoes themselves represent Germany's most advanced underwater weapon technology. The primary weapon is the G7ET-11 Zaunkönig 2 acoustic homing torpedo, designed to lock onto propeller noise from escort vessels and pursue targets without further guidance. The T-11 uses passive acoustic detection immune to Allied Foxer noise-making decoys that successfully defeated earlier German acoustic torpedoes. Additionally, the Type 21 carries loop pattern running torpedoes programmed to execute complex zigzag courses through convoy formations, maximizing hit probability against densely packed merchant ships. Fire control represents another revolutionary advance. The GHG passive sonar system, the most sensitive underwater detection equipment on any World War II submarine, mounts in a retractable balcony beneath the keel. This installation provides 360-degree acoustic coverage without the flow noise that compromises hull-mounted arrays. The GHG can detect individual ship propeller signatures at ranges exceeding 30 nautical miles under favorable conditions, providing targeting data long before visual contact becomes possible. The sonar feeds directly into a specialized plotting table and fire control computer that automatically calculates torpedo firing solutions based on target bearing, range, speed, and course. The commander simply selects targets and fires. The system handles all ballistic calculations, eliminating the manual trigonometry and estimation that introduces error in conventional submarine attacks. For detection and navigation, the Type 21 carries FUMO 65 Hohentuil radar, effective for surface search when snorkeling, but more importantly, for detecting Allied radar transmissions, before they detect the submarine. The radar warning receiver, codenamed Tunis, provides 360-degree coverage across all Allied radar frequencies, giving commanders seconds of warning before aircraft arrive overhead. Combined with rubber-based anechoic coating applied to the hull and sail to absorb Allied sonar pulses rather than reflecting them, the Type 21 possesses stealth characteristics decades ahead of its time. The crew accommodations represent equally dramatic improvement over earlier U-boats, where submariners endured conditions barely distinguishable from punishment. The Type 21 carries 57 crew members, substantially more than Type 7 boats, with 44 to 52, but provides vastly superior living conditions. Individual bunks replace the hot bunking system where crew members share sleeping accommodations with different men using the same bunk across different watch rotations. A shower facility, unheard of on earlier boats, where crew members might go weeks without bathing, provides basic hygiene capability. A freezer allows storage of fresh food, rather than relying entirely on canned provisions and dried goods. These improvements matter not for comfort, but for combat effectiveness. Crew fatigue and malnutrition contributed significantly to declining performance on extended patrols. The Type 21's accommodations allow longer patrols while maintaining crew alertness and health. But the transformation from revolutionary design to operational reality encounters problems that ultimately prevent the Type 21 from affecting the war's outcome. The decision to skip prototype development and proceed directly to mass production, driven by strategic urgency, creates a cascade of quality issues that plague every boat constructed. Albert Speer's armament ministry, following Dönitz's directive to maximize production speed, contracts prefabricated hull sections to companies with minimal shipbuilding experience. Sections are manufactured at inland facilities, including several using forced labor from concentration camps. The workers, often unskilled and working under brutal conditions, cannot maintain the precision tolerances required for submarine construction. When sections arrive at final assembly shipyards, the problems become immediately apparent. Bulkheads do not align properly between sections manufactured at different facilities. Piping connections are mismatched by millimeters, requiring custom fabrication to connect systems spanning multiple sections. Hydraulic lines show installation errors that create leak points under pressure. Electrical systems lack proper insulation at junction points. The streamlined external hull panels arrive with surface irregularities that compromise hydrodynamic performance. Each submarine requires extensive post-assembly work to correct defects, eliminating the time savings that modular construction was supposed to provide. More fundamentally, the lack of prototype testing means every boat serves simultaneously as test platform and operational vessel. The hydraulic torpedo loading system, never proven in actual sea trials before production begins, proves mechanically unreliable with frequent valve failures and accumulator pressure losses. The complex hydraulic system places critical components including pumps and accumulators outside the pressure hull for accessibility during maintenance. But this positioning makes them vulnerable to corrosion from seawater and damage from combat. The snorkel system, essential for the Type 21's operational concept of remaining submerged continuously, uses a design poorly suited for North Atlantic conditions, where heavy seas frequently wash over the snorkel head, triggering automatic valves that momentarily cut air supply to the diesel engines and create dangerous pressure fluctuations inside the boat. The engines themselves present problems. The MAN diesels, while producing adequate power, prove underpowered relative to the submarine's displacement. Surface speed barely exceeds 15 knots, substantially slower than the 18 knots typical of earlier U-boats. This limitation increases battery charging time because generating capacity depends on engine power. A Type 21 at schnorkel depth requires 5 hours to fully charge batteries versus the 3 hours originally specified, extending the period when the submarine remains vulnerable to detection by radar-equipped aircraft. But the most catastrophic problem is timing. Production begins in 1944, but the assembly process moves far slower than optimistic projections suggested. The first Type XXI, U-2501, is launched from Blohm+Voss shipyard in Hamburg on May 12, 1944. But launching is not commissioning. Extensive fitting-out work follows, installing equipment, testing systems, and correcting defects discovered during construction. U-2501 is commissioned on June 27, 1944, 18 months after design finalization, versus the 6 months predicted by modular construction advocates. Throughout late 1944 and early 1945, Type XXI boats are launched in substantial numbers. By March 1945, 118 boats have been completed and commissioned. But completion does not equal combat readiness. Each boat requires sea trials to identify and correct remaining defects, followed by crew training on unfamiliar equipment. The training process alone requires months. Crews must learn the hydraulic systems, master the advanced fire control equipment, and develop tactical procedures for a submarine that operates completely differently from conventional boats. The training pipeline faces additional obstacles from Allied actions. By mid-1944, the Baltic Sea, Germany's primary submarine training area, becomes increasingly hostile. RAF Coastal Command launches intensive mining campaigns, sowing acoustic and magnetic mines across waters where U-boats conduct diving trials and weapons testing. Between August 1944 and April 1945, 12 Type XXI boats are lost to mines, aircraft attacks, or accidents during training, never firing a shot in combat. The advance of Soviet forces along the Baltic coast further constrains available training areas, compressing submarine operations into increasingly confined waters under constant Allied air surveillance. Industrial facilities suffer parallel degradation. Blohm+Voss shipyard in Hamburg, primary constructor of Type XXI boats, endures repeated heavy bomber raids throughout 1945. Attacks on January 17th, March 11th, March 25th, and April 9th cause direct damage to assembly facilities, destroy specialized tooling, and kill skilled workers. Indirect effects prove equally damaging. Power outages halt production for days. Workers arriving for shifts find their homes destroyed, forcing time away to relocate families or search through rubble. Transportation networks disrupted by bombing make it difficult for workers to reach shipyards even when facilities remain operational. The bunker at Farge, intended as a bomb-proof final assembly facility for Type XXI boats, represents Germany's most ambitious attempt to protect submarine production from Allied bombing. Construction begins in 1943 using approximately 10,000 forced labourers, primarily concentration camp prisoners and prisoners of war. The facility's reinforced concrete roof measures 7 meters thick, designed to withstand direct hits from conventional heavy bombs. But in March 1945, before any submarines are assembled there, RAF Bomber Command attacks using Grand Slam earthquake bombs, massive 22,000-pound penetrators that create seismic shocks destroying underground structures. The bunker, 90% complete, is abandoned. By April 1945, as the Third Reich collapses and Allied armies close on Germany from both east and west, 118 Type XXI boats have been commissioned, but only 4 are certified combat-ready. The training pipeline, quality control process, and crew assignment system have completely failed to transform manufactured hulls into operational weapons. The vast majority of Type XXI submarines never leave port, lacking either functional equipment, trained crews, adequate fuel, or some combination of all three. Only 2 Type XXI boats conduct operational war patrols, both in the final weeks before Germany's surrender. U-3008, commanded by Captain Lieutenant Helmut Mansek, departs Wilhelmshaven on May 3, 1945, as Allied artillery fire can be heard from advancing ground forces. The patrol lasts just days. U-3008 encounters a convoy in the North Sea, makes an approach pass underneath the ships while submerged, demonstrating the advanced submarine can penetrate escort screens undetected, then receives the ceasefire order on May 4th and returns to port. No torpedoes fired, no ships sunk. U-2511's patrol, commanded by Adelbert Schnee, provides the only operational validation of Type XXI capabilities. Schnee brings exceptional credentials to this mission. Over 12 previous patrols in conventional U-boats, he sank 26 merchant ships, totaling approximately 90,000 tons, earning the Knight's Cross with oak leaves and recognition as one of Germany's most skilled submarine commanders. When U-2511 commissions on September 29, 1944, Schnee and his carefully selected crew represent the elite of what remains of the Kriegsmarine submarine force. The boat completes working-up exercises in the Baltic through winter 1945, testing equipment and training crew on systems that differ fundamentally from conventional submarines. On March 16, 1945, U-2511 departs Kiel for Norway, officially becoming the first Type 21 to deploy on a combat flotilla. But mechanical problems plague the transit. Periscope damage during deep diving trials at Horten requires repairs. Diesel engine malfunctions force diversion to Bergen on April 21st for additional maintenance. Not until April 30th, 1945, the day Hitler commits suicide in Berlin as Soviet forces close on his bunker, does U-2511 finally depart Bergen on her operational war patrol. The intended destination is the Caribbean, an ambitious cruise designed to test the submarine under every possible operational condition across thousands of miles of ocean. The patrol demonstrates immediately that Type 21 performance specifications are not propaganda, but reality. On May 2nd, U-2511 detects an Allied anti-submarine warfare group north of Scotland. The hunter-killer force, likely centered on an escort carrier with destroyer screen, represents exactly the threat that proved lethal to conventional U-boats. They detect U-2511 on sonar and close for attack. But when they launch depth charges and attempt to maintain contact, the Type 21 simply accelerates underwater to 17 knots and escapes. The destroyer escorts, capable of perhaps 24 knots maximum in moderate seas, cannot maintain pursuit against a target sprinting away underwater. The depth charges explode helplessly hundreds of yards astern, as expanding circles of possible locations outpace available search resources. Then comes May 4th, and the encounter that validates everything German engineers claimed for this design. U-2511, operating submerged northwest of the Shetland Islands, detects HMS Norfolk through the GHG passive sonar array. Schnee closes at high speed, covering miles while remaining entirely underwater, then slows to silent running and penetrates the destroyer screen surrounding the cruiser. The passive sonar provides precise targeting data. The fire control computer generates a perfect attack solution. 6 tubes loaded and ready. At 500 meters range, a salvo of T-11 acoustic homing torpedoes would almost certainly result in multiple hits on the 10,000-ton cruiser. But Schnee has already received the ceasefire order transmitted 3 hours earlier. Germany has surrendered. Admiral Dönitz, now serving as President of the Reich following Hitler's death, has ordered all U-boats to cease offensive operations immediately. Schnee makes the approach as a training exercise, proving the Type 21 can accomplish what Allied anti-submarine forces believed impossible. He penetrates an escort screen in daylight. He achieves ideal firing position without detection by the most advanced Allied sonar equipment. He demonstrates that the submarine designed to reclaim Atlantic dominance functions exactly as intended. Then he dives deep, engages the silent running motors, and departs the area without firing. HMS Norfolk and her escorts never detect his presence. The submarine that could have won the Atlantic War arrives for its first kill just hours after that war ends. U-2 511 surfaces and transmits her position on May 5th. She reaches Bergen that same day. When Schnee meets officers from HMS Norfolk days later to surrender his boat, the British initially refused to believe U-2 511 approached within 500 meters undetected. Their sonar operators reported nothing. Their depth-charge teams never launched weapons. The first they knew of the German submarine's presence was when she surfaced and transmitted surrender. Modern historical analysis questions some details of Schnee's account, noting inconsistencies in his log and suggesting the encounter may have occurred differently than he claimed. But regardless of specific details, the fundamental reality remains undisputed. U-2 511 operated off Scotland for days, evaded Allied hunter-killer groups, and returned to port undetected until she chose to reveal her location. No conventional U-boat could have accomplished this in May 1945, when Allied anti-submarine warfare had reached peak effectiveness. The two brief operational patrols by U-3008 and U-2511 sink 0 Allied ships, but provide decisive proof that the Type XXI design functions as intended. The remaining 116 commissioned boats never deploy. In the war's final days, 81 Type XXI submarines are scuttled by their crews, destroyed in port, or captured incomplete by advancing Allied forces. 11 operational boats in Norway surrender to the Allies, along with several more at German ports. The revolutionary submarines that might have changed history become war prizes distributed among the victorious powers. The post-war scramble to examine captured Type XXI boats reveals that every major naval power recognizes immediately what Germany developed. The United States acquires 2 boats, U-2 513 and U-3 008. They are sailed across the Atlantic by American crews assisted by German sailors to translate equipment labels, arriving at the submarine base in New London, Connecticut, in August 1945. The US Navy's Board of Inspection and Survey issues a comprehensive 185-page report titled Former German Submarines in April 1946, documenting every technical detail from hull construction to fire control systems. The report contains both praise and criticism. Naval architects admire the streamlined hull design and integrated battery installation. The hydraulic torpedo loading system impresses American observers despite its mechanical complexity. The passive sonar array demonstrates capabilities superior to American equipment, but the assessment also identifies serious flaws. The diesel engines prove underpowered relative to submarine displacement. The hydraulic system's vulnerability to damage when critical components mount outside the pressure hull represents a design error American submarines would not repeat. The snorkel design lacks sophistication compared to systems American engineers were already developing independently. Most critically, post-war inspection reveals that rushed wartime construction left structural weaknesses throughout the captured boats. Welds show inadequate penetration. Hull plating displays variations in thickness. Assembly quality falls far below American submarine construction standards. But flaws do not diminish the fundamental significance of what Germany achieved. The Type XXI represents the first true submarine, designed from inception to operate underwater rather than on the surface. Every diesel-electric submarine designed by any navy in the 2 decades following World War II derives directly from Type XXI concepts. The Soviet Whiskey class, backbone of the post-war Soviet submarine fleet with 236 boats constructed between 1951 and 1958, copies the Type XXI's hull form and battery arrangement almost exactly. The American Tang-class submarines, commissioned between 1951 and 1952 as the US Navy's first post-war attack submarines, incorporate streamlined design principles and integrated battery installations pioneered by Germany. The British Porpoise class, entering service in the mid-1950s, uses similar hull cross-sections and propulsion arrangements. Even the Swedish Hagen-class submarines built in the 1950s derive from Type 21 technology. The influence extends beyond diesel-electric submarines. USS Nautilus, the world's first nuclear-powered submarine commissioned in 1954, uses a modified Type 21 hull form, optimized for high-speed underwater operations. The nuclear reactor replaces diesel engines and batteries, eliminating the need to surface or snorkel for air. But the hydrodynamic principles remain those proven by Germany's Elektroboot. Every submarine operating today, whether nuclear or diesel-electric, traces its design lineage to the Type 21. The counterfactual alternative haunts strategic analysis of the Battle of the Atlantic. If Type 21 submarines had entered service in significant numbers during 1943, when the Atlantic campaign reached its critical phase, could Germany have altered the war's outcome? The question generates endless historical debate, but the mathematics suggest plausible scenarios where deployment timing changes strategic realities. In March 1943, German U-boats achieved their greatest success, sinking 82 merchant ships in the Atlantic, totaling 476,000 tons. Allied shipyards during this period construct approximately 140 Liberty ships monthly, each carrying 10,000 tons of cargo, maintaining slight advantage in the tonnage war. But these successes use conventional submarines. Now consider March 1943 with 50 Type 21 boats operational. Each Type 21, with its ability to fire 18 torpedoes rapidly at single convoy encounters, its capacity to evade hunter-killer groups through superior underwater speed, its extended patrol endurance allowing weeks on station without surfacing, represents combat potential perhaps 3 times greater than conventional boats. 50 Type 21 submarines deployed against North Atlantic convoys could plausibly sink 200 merchant ships monthly, doubling German effectiveness and exceeding Allied construction capacity. The tonnage war arithmetic shifts decisively in Germany's favour. Allied convoys would require triple the escort forces to provide adequate protection against submarines that can approach undetected, fire multiple salvos rapidly, and escape pursuit through underwater sprinting. But escorts are limited resources. Destroyer escorts and frigates required for convoy protection come from the same shipyards building merchant ships. Tripling escort requirements means reducing merchant construction or leaving convoys inadequately protected. Furthermore, the Type 21's extended underwater endurance nullifies Allied advantages in signals intelligence and radar coverage. Ultra-decrypts of German naval codes allowed Allied command to route convoys around known U-boat positions, reducing encounter rates dramatically. But this advantage assumes U-boats must transmit radio reports frequently, revealing positions to Allied direction-finding networks. Type 21 submarines could maintain radio silence for weeks, proceeding to patrol areas on sealed orders, remaining undetectable until they attack. Centimetric radar revolutionized anti-submarine warfare by detecting surfaced U-boats before they detect aircraft. But Type 21 boats never surface in patrol areas, eliminating radar's effectiveness. The strategic implications extend beyond shipping losses. If Germany maintains pressure on Atlantic supply lines through 1943 and into 1944, the build-up for D-Day becomes problematic. Operation Overlord requires transporting 150,000 troops, plus equipment, vehicles, ammunition and supplies across the English Channel. But before D-Day, those resources must reach England from the United States via Atlantic convoys. Delaying or reducing the flow of supplies to Britain postpones invasion preparations, potentially pushing D-Day from June 1944 to late 1944 or even 1945. Every month of delay provides Germany additional time to complete Atlantic wall fortifications, position reinforcements, and potentially develop other wonder weapons, including jet aircraft and improved missiles. However, this counterfactual assumes Germany could actually produce Type 21 submarines in significant numbers by 1943, an assumption that confronts multiple obstacles. The decision to finalize the Type 21 design comes in January 1943. Even with aggressive timelines, production cannot commence until mid-1943 at earliest. Quality problems stemming from rushed development without prototype testing would affect any boats built, regardless of timing. The industrial capacity required to construct large submarines competes with aircraft production, which Hitler prioritizes consistently. Specialized components, including high-capacity batteries, advanced sonar arrays, and hydraulic systems, require manufacturing expertise and materials in limited supply. Most critically, Germany lacks the industrial advantage that allows the United States to outproduce Axis powers across every category of military equipment. American shipyards construct 2,710 Liberty ships during the war, averaging 45 days from keel laying to launch using assembly line production methods. German shipyards, even under optimal conditions, require 6 months minimum to construct a Type 21. The United States commissions 475 new submarines during World War II. Germany launches 1,162 U-boats of all types, but many are lost before completion, and quality varies dramatically. The industrial mathematics that doom Germany's conventional submarine campaign would eventually doom Type 21 production as well, simply at a later date. But later date matters tremendously in warfare. If Type 21 submarines force Allied command to divert substantial resources to enhanced anti-submarine warfare in 1943 and 1944, those resources come from other priorities. Escort carriers assigned to hunter-killer groups cannot support amphibious operations in the Pacific. Destroyer escorts protecting convoys cannot support bombardment missions before Normandy beaches. The indirect effects cascade throughout Allied strategic planning. Germany loses World War II regardless of Type 21 deployment timing, but the margin of defeat and the timing of surrender could differ substantially. The legacy of Germany's revolutionary submarine extends beyond hypothetical alternate histories to concrete technical influence on post-war naval development. One Type 21 boat, U-2540, survives the war in unusual fashion. Scuttled by her crew in shallow water off the German coast in May 1945, she remains underwater until 1957, when West Germany's newly formed Bundesmarine raises and refurbishes her as research vessel Wilhelm Bauer. The submarine operates in military and civilian research roles until 1982, providing German naval architects with opportunity to study their own revolutionary design and apply lessons to modern submarine development. In 1984, Wilhelm Bauer opens as a museum ship at the German Maritime Museum in Bremerhaven, where she remains today, the only preserved Type 21 and a tangible reminder of technology that arrived too late to affect its intended war. The French Navy operates U-2518, renamed Roland Moriot, through the 1950s and into the 1960s. She sees active combat during the 1956 Suez Crisis, finally providing operational validation of Type 21 capabilities 2 decades after the design's original purpose. The Soviet Union receives 4 Type 21 boats and uses them as the direct template for the Whiskey-class submarine program, the largest submarine production run in history. Between 1951 and 1958, Soviet shipyards construct 236 Whiskey-class boats, providing the submarine backbone of the Soviet Navy through the Cold War's early decades. Everyone derives from German engineering captured in 1945. The technical lessons extend to details. The anechoic rubber coating developed for Type 21 hulls to absorb sonar pulses becomes standard on all Cold War submarines. The Figure 8 pressure hull cross-section optimizes internal volume while maintaining strength, appearing on Soviet, American, British, and French submarines throughout the 1950s. The concept of integrated battery banks forming structural hull components rather than separately installed equipment influences every diesel-electric submarine designed in the post-war period. Even the Type 21's flaws provide valuable lessons. The problematic hydraulic torpedo loading system teaches that mechanical complexity must be balanced against reliability under combat conditions, a principle that guides later automated weapons handling systems. Perhaps most significantly, the Type 21 validates the fundamental concept that future submarines must be designed for underwater operations first, with surface capabilities treated as secondary considerations. This principle seems obvious in retrospect, but represented revolutionary thinking in 1943, when navies worldwide viewed submarines as surface torpedo boats that temporarily submerge. The Type 21 proves that a properly designed submarine can outperform surface vessels in every tactical parameter except surface speed, which becomes irrelevant when the submarine never surfaces. This insight drives submarine development for the next decade until nuclear propulsion eliminates remaining constraints on underwater endurance. The story of the Type 21 ultimately demonstrates that technical excellence without adequate timing produces historical footnotes rather than strategic impact. The submarine incorporates revolutionary innovations that define the next generation of underwater warfare. The design functions exactly as intended when finally deployed operationally. Individual boats demonstrate performance that validates every claim German engineers made. But innovation arriving in May 1945 cannot affect battles decided in 1943. The mathematics of industrial production, the importance of prototype testing, the complexity of training crews on unfamiliar equipment, and the effects of Allied strategic bombing all combine to ensure that Germany's revolutionary submarine reaches operational status just weeks before surrender makes operational status irrelevant. The forgotten heroes of the Type 21 program are not the commanders who conducted brief patrols in war's final days, but the engineers who designed a technically successful submarine under impossible time constraints. The shipyard workers who constructed sophisticated vessels despite bombing raids and material shortages. And the crew members who trained on unfamiliar equipment, knowing their boats would almost certainly never fire shots in combat. They created something genuinely revolutionary that influenced naval architecture for decades, but they created it too late. The war ended not because Germany lacked technical innovation, but because technical innovation alone cannot overcome strategic disadvantages in industrial capacity, geographic position, and accumulated Allied advantages from earlier battles. The Type 21 represents what might have been. A submarine that could have won the Atlantic War. A design that could have changed the outcome of the most critical campaign in the European theatre. A weapon system that arrived 3 weeks before surrender, when 3 years earlier might have altered history. The bitter irony is that everything worked. The revolutionary hull design performed as predicted. The triple-capacity batteries provided extended underwater range. The hydraulic torpedo loading enabled rapid salvo firing. The advanced sonar detected targets at unprecedented ranges. The silent running motors made detection nearly impossible. When Korvettenkapitän Schnee approached HMS Norfolk on May 4, 1945, achieving perfect firing position undetected by the most sophisticated anti-submarine forces in the world, he proved conclusively that the Type 21 could do everything German engineers promised. But proving a concept in May 1945 changes nothing about March 1943, when the Atlantic War reached its crescendo and the Type 21 existed only as blueprints in occupied Paris. The submarine that would have won the Atlantic arrived too late. Not because the design failed, but because wars are won by adequate equipment deployed in adequate numbers at the decisive moment, not by revolutionary equipment deployed in inadequate numbers after the decisive moment has passed. The Type 21's legacy lives on in every modern submarine, but its purpose died unachieved when U-2511 chose not to fire on a cruiser she could have destroyed because the war it was built to win had already ended hours before.